Hi, and welcome to this discussion of atmospheric dynamics. This is our fourth video on the vorticity equation. In this video, we're going to talk about the applications of the scaled vorticity equation. So here's your scaled vorticity equation. We got rid of a bunch of terms. We had 4 terms to start with. We're down to 2 terms right now. The 2 terms we're looking at is the relative vorticity, the change in relative vorticity following the parcel, and the other term is the divergence term. So we got rid of all the other terms, the ones that were not important on the synoptic scale. So we're going to apply this. We're going to see how this affects error, if there's convergence or divergence as you move along with a parcel of error. So here's an upper level wave pattern. Let's say that this is 500 millibars. You got trough and 2 ridges. We're going to watch the air flow through the troughs and ridges. So there's our airflow, and we're going to assume that there's no shear, and the only vorticity that results is from curvature, and that's all. And that's not always the case, but let's make that assumption. It makes things a little bit easier and a little bit simpler. So I've put a parcel in the flow. It looks like a golf ball. We're going to move that parcel of air through this 500 millibar flow. As it moves from the ridge to the trough, that means that it's going from an area of minimum vorticity. Remember that ridges have minimum vorticity or even negative vorticity, and troughs have positive cyclonic vorticity. So that means as you go from the ridge to the trough, the vorticity is increasing following that parcel. This is Lagrangian flow moving along with the parcel. So if we look at our scaled vorticity equation, if the left-hand side is positive, what do we need to do to make the right-hand side positive? Well, number one, F, the Earth's vorticity, is always positive in the northern hemisphere. So we got a minus sign outside to make that right-hand side positive. That means that we need to have a delta that is negative. And a negative delta, one that's less than 0, means that there's convergence. So at 500 millibars, as the wind flows from the ridge to the trough, upstream of the trough, we have convergence in the upper levels of the atmosphere. So if you have convergence in the upper levels of the atmosphere, that must mean that you have sinking motions and divergence in the lower layers of the atmosphere. Convergence results in sinking motions in the upper levels because you've got a tropopause that is very stable, that doesn't allow air to exchange or go through the tropopause, so it acts as kind of a lid. So upper level convergence results in sinking motions and lower level divergence. And as a result, of course, you would expect clear skies. Let's just look at the other case where we're moving from a trough to a ridge. So moving from a trough to a ridge, of course, the trough has a maximum in curvature vorticity, relative vorticity there. As you move towards the ridge, you're moving to a region that has a minimum of vorticity. So that means that your vorticity is decreasing with time. The spin is spinning down, actually. The air is spinning down. And because of that, if that's negative, if the left-hand side is negative, the right-hand side needs to be negative. How does that become negative? Well, you got a minus sign out there. F is always positive, so that must mean that delta is positive to make that right side positive. A positive D means divergence. So we have divergence aloft. And because of the tropopause is a lid on the atmosphere, if it's diverging aloft, that must mean you have rising motions and convergence to lower levels of the atmosphere. Now, if that air had any kind of moisture as it's forced to rise, it will condense and produce clouds. So you have cloudy skies with rising motion. So this is what you typically see on a weather map. This is a 500 millibar map, and looking downwind of the trough, you can see on the radar summary chart that there's lots of precipitation caused by, of course, rising motion in the atmosphere. So this is a rule of thumb. Looking downwind of troughs, you're going to see rising motions, and typically you're going to see clouds and precipitation. In the next video, we're going to talk about jet streams and how you can infer rising and sinking motions with jet streams using vorticity.